At the end there should be a P which has got cut in the scanning, I think. Okay. So, no, P is here. So, do not worry, P is there. Okay. So, if you want to apply these rigid body motions successively, then what will you do? You will first multiply this vector with the rotation matrix, add to that the translation vector, that becomes a new point. That new point multiplied by this matrix and this vector added to it, that will be the next point, next new point, that is after the second rigid body motion. Then there is a third rigid body motion. You intend to go on moving from here to there, there to there, there to there, there to there, and finally grab something. Okay. So, how many such things you will have to do, and that big expression, very funny expression, and it will, you will lose track of it. So, this is the formulation bottleneck of this representation, and there is a very quick clear remedy out of it, and the remedy is this, that extend P with one extra dummy 1 and extend similarly P prime also with a dummy 1, that is, rather than writing x y, write x y and 1 similarly here, and then this here you pack together all the things that you needed. You needed rotation matrix R, put it here 2 by 2. You needed the translation vector T x T y here, put it there just beside it, and then below that put 2 zeros here and a dummy 1. So, this entire fourth row is dummy in this. Now, if you open it, it looks like this, and as you compare, you find everything is in proper place. That is, directly if you compare. So, from the upper row block you will get P prime equal to R P plus T, that is correct, and from the lower block you will get 1 equal to 0 plus 1, which is true, you do not care about it, that was dummy anyway. Okay. So, now you can say that this whole thing is equal to just a matrix multiplication with this whole thing, and now when you want to compose like that, you will go on pre-multiplying T 1, T 2, T 3, T 4. Okay. The rotation which we saw just now, that was in 2D, but our space is actually 3D. So, as it was happening in the 3D space, that rotation was taking place in the xy plane, okay, and you call that a rotation about the z axis. So, that z axis was there, okay, but the rotation was taking place in xy plane. So, the same representation you can extend to 3D, in which z coordinate does not change, the remaining two change according to whatever we discussed earlier. When you pack up all these three together, you get this, and this then you say is the rotation in the xy plane or rotation about the z axis equivalent. Okay. Similarly, you can talk of rotation about x axis and y axis. And you can then talk about rotation about some other axis. Okay. So, in rotations, composition rule is, that is for successive rotations, if the frame of reference is fixed as we earlier considered, then the point is on this side. So, on the point first rotation R1 is applied, then R2, then R3 and so on. So, the successive rotation matrices will be pre-multiplied like this. On the other hand, if the thing that is rotating, the frame of reference in which all the things are expressed, that is fixed to that body, then you can show that it turns out to be exactly the other way around. Okay. So, this is the composition rule for rotation matrices. All these things you have seen already. Now, we go back to this thing again and consolidate what we have done till now. So, translation and rotation we represent like this. Now, this is a 3 dimensional vector T. Now, actually with a dummy 1 it will become 4 dimensional. Okay. So, this dummy 1 is here, and then this is 3 by 3 matrix sitting here, below that a row of dummy zeros 0 0 0 and this whole thing. Then you can say that the new point with this extra one hanging below it is equal to this 4 by 4 matrix into the old one with a similar one hanging below. Okay. Now, this 3 by 3 matrix, in that it is orthogonal. So, you can say that these are analogous to x, y and z unit vectors of some coordinate frame. Okay. So, that is the coordinate frame where the base coordinate frame would go when you give that rotation. Okay. And this entire matrix is called homogeneous transformation matrix. Okay. This figures in the robot kinematics again and again in several rows. Okay. And now, composition of several rigid body motions referring to the fixed frame will be done like this, and referring to the body which itself is going through those motions is this. You have already given one rigid body motion to a body, and now that was represented like this matrix sitting inside. Okay. Now, you want to bring it back. In order to bring it back, you have to give the inverse transformation. For that, you can readily compose the inverse, which is this. Okay. So, the rotation part will be the inverse or transpose of the old one, and the translation part will be this. Any questions till now? Till now everything is fine? Now, this is something to keep in mind, that the rotation matrix as well as the 4 by 4 homogeneous transformation plays a dual role. That is, on one side this matrix represents an actual rotation of a rigid body with respect to a frame, and the same matrix will represent the orientation of a frame with respect to another. What is the idea that I am trying to express? This is a frame of reference. Okay, fixed, and then in that, now in this frame of reference, the origin of which is perhaps at that corner, and x axis is along that direction, y axis is along this direction, and z axis is perhaps vertically upward, and that is fixed to this room. Okay. Now, a chair is placed there, okay, at the corner, okay, with one side of the chair touching that wall, another side touching this wall, and the person sitting vertically anyway. That is the way people sit. Okay. And to that chair another frame of reference is attached. Okay. Room is not going to move, but the chair can. We move the chair. Okay. We turn the chair like this. As we do that, this x axis goes here, this y axis goes here, and this z axis goes somewhere. Okay. That may be a troublesome business, because one of the things has to go inside the wall, but let us do it. Okay. This rotation matrix, when multiplied to the original orientation of these two things, these three things x, y and z, okay, originally these were the three unit vectors, okay, or any vector in that chair. Okay, any vector in that chair was originally something Now, when you multiply this rotation matrix, then you get the chair in this new orientation. This the rotation matrix is representing, it is representing an actual rotation. Okay. At the same time, after the chair has rotated, if you need to describe its orientation in the fixed frame, then you will ask in what orientation the chair is right now configured, and the answer is the same rotation matrix will describe its orientation, because the first column of that rotation matrix will show its location of the x coordinate here, second column will show the orientation of the y coordinate, and the third column will show the location orientation of the z coordinate, okay, z direction. So, the same 3 by 3 orthogonal matrix that represents an actual rotation will also represent the orientation of the rotated body. Okay. Fine, we continue. And similarly, the dual role of the homogeneous transformation is that the same 4 by 4 transformation matrix, homogeneous transformation, that represents an actual rigid body motion will also represent the position and orientation of the body after that motion has taken place. Okay. Now, we come to robot kinematics. A typical a typical manipulator or any kind of robot will have links in series connected through joints. Okay. And what is important is to be able to represent the position and orientation of one of those bodies with respect to another. Okay. So, suppose link I minus 1 is connected to link I through this joint. Okay. Similarly, the previous link in the series I minus 2 is connected to link I minus 1 through this joint, which is axis I minus 1. Axis I minus 1 is a line in 3 dimensional space. Axis I is another line in the 3 dimensional space. In 3 dimensional space, when you talk of two lines, how are the ways they can be disposed to against each other? They can be intersecting, they can be parallel. Okay. Most general, skew. So, in general they can be skew. Okay. So, that is what you expect. So, one passes like that, another passes like this, and in that case there will be a perpendicular distance between them, with one foot of perpendicular at this end, the other foot of perpendicular at that end. That plays an important role, and compared to this line, this axis, this joint axis, if you want to represent this joint axis along with the corresponding frame of reference, then you will need 4 numbers, 4 quantities. Those are the most important numbers in manipulator kinematics. Say this frame is already there, that is, with this link I minus 1, you have attached already a frame. One rule that we invariably follow is that the z axis of the frame is along the axis of the joint, and when I say axis of the joint, it is the axis of rotation or translation. Always depends upon what kind of joint it is. If it is a revolute joint, if it is a rotary joint, then it is the axis of the rotation. On the other hand, if it is a sliding joint, okay, then it will be translation, direction of the translation. So, the z axis is always along the axis of rotation or direction of translation. Okay. The question is how to put the other two axes and where to put the origin, because after fixing the z axis of the frame, you can take the origin anywhere. Okay. So, now you say that with the next axis you identify the common perpendicular, and at the foot of that perpendicular you place the origin, and along that common perpendicular you place the x axis. Okay. After fixing these two, how to fix the y axis? Right hand rule, nothing, it is already fixed, we have to just know it. Okay. So, you take this unit vector cross this unit vector, you get this unit vector, done. Then we go here, and then we say what about the next one. Okay. So, next z axis is already known, okay. Origin is not known, origin has to be fixed. So, for that between the axis I and the axis I plus 1 we have to do the similar thing, fix the origin, fix the x axis, and accordingly y axis will get settled, and all these things we can do in a series of links from one axis to another axis to another, and so on, we can do that. Now, we can fix frames of references. Now, we say that how to represent the position and orientation together called pose of this frame of reference with respect to this frame of reference expressed in this frame of reference. That is, if somebody sits here at this frame of reference and tries to find out where is that point, then he has to say a distance x coordinate along this direction, y coordinate along this direction, z coordinate along this direction, which will place this point. Okay. That will be the fourth column of the transformation matrix in the description of the pose or position and orientation in the homogeneous transformation. And then you have to say then what is the description of the x axis of this frame, that is this unit vector, what is its description in this x y z. So, some 0.75 in this direction, 0.32 in this direction, and something 0.23 in this direction, whatever it is. So, whatever it is this, whatever is this, whatever is this, they will frame the 3 columns of the rotation matrix in the transformation matrix. So, how to determine those things? Okay. So, in order to determine that, you say how to go from here to here. Suppose we leave one copy of this frame of reference here and take the other copy with us from here through successive motions well regulated, so that ultimately we come here. Okay. We coincide with this. So, for that what you have to do? First you move this along this, or first you can align the x axis, you can do it either way. Which one you want to do first? Rotate first, no problem. So, leave a copy of this frame of reference here, and the other copy you turn about its z axis, okay, through an angle such that this fellow becomes parallel to this fellow, x's become parallel. Okay. So, that angle, that is actually this angle. Okay. So, you see parallel to this I have drawn one along this red, and between these two the angle is alpha I minus 1. It has been shown on the back side because on that side not enough space was there. Okay. So, fine. So, by that alpha I minus 1 you turn this frame about the z axis, so that this x turns and comes like this and becomes parallel to that. Okay. Then x, as x turns, y also will turn, x will become parallel to this, y will become somewhere something you do not know. Okay. And then that frame of reference you can move along the x axis till this point. Okay. Along the x I minus 1, okay. You move along this till this point. Okay. And then what happens? Then you have got the z here x parallel, and then you can move the thing along this, or you could have done those two things. No, this movement is not about the z axis, this movement is about the x axis, sorry. this movement is about the x axis, because this one is going to turn the z direction. Okay. So, this is perpendicular to this, na? This is perpendicular to this. Okay. So, y z actually turns. Okay. So, through the movement along about the x axis, it is the z axis which will turn and become parallel. About when you rotate it about the x axis, this z moves through this and becomes parallel to this z axis. Okay. So, z becomes parallel, and now when you move it till this point, the z's coincide. Okay. You could have done it the other way around also, that is, first move it along the common perpendicular. So, this z comes here and then rotate it about this common perpendicular x, so that the z becomes coincident, and then move it along the z now here till this point to the next common perpendicular foot of the common perpendicular, and then turn it about the z in order to align x y. So, in the first step, if you move it till this point, then the skew lines become intersecting. Okay, this line comes here. Then when you turn it about the common perpendicular about the x axis, then this becomes this z axis coincides. Then as you move it along this line about the local z axis, then you come here, origins coincide, x and y are still different in the same plane. Then about this z axis, you turn again through an angle to get the x axis coinciding. So, these 4 steps you have to do, and accordingly the distances moved and angles turned are the 4 parameters that you need to describe this motion. So, the angle alpha through which you turned about the x axis is called the twist angle, and the distance of the common length of the common perpendicular, that is called the link length. That makes sense, because if the whole thing were planar, then all of them, all the axes would be parallel, thinking it is rotary. Okay. And the alpha is actually showing how much one axis is twisted away from the other one. Okay. So, how much is the plane of that twisted away from the original plane. So, that is why it is called twist angle, and this common perpendicular, that is actually in a way the distance between the two axes, and that is why that is called the link length. And wherever you came here, from that how much you need to go along the axis to get to the next frame. So, that is why it is called frame offset. And finally, how much you have to turn, that is the joint angle of this joint. Okay. So, these are the 4 DH parameters, Denavit-Hartenberg parameters, out of which 3 are always fixed by design. These 2 will always get fixed by design. Okay. This will be fixed by design and if the joint is revolute, and in that case this will be the free variable, by moving which, by changing which you will accomplish the movement of the robot. On the other hand, if the particular joint is translating, that is prismatic joint, then this will be fixed by design and this will be the variable. Okay. Now, note that we were giving all the motions here about the local frame. Okay. So, we took a copy of that and went through successively this, which was about its local frame. That is why we go on post multiplying. Okay. Rotation and translation, 2 rotation matrices, product is typically not commutative. One rotation, one translation also typically in general not commutative, but if the rotation is about a particular axis and translation is also along that same axis, then that can be interchanged. So, these 2 could be interchanged in order, these two could be also interchanged in order, but nothing else. So, when you put all those 4 things, then they will look like this. The product of these two in whichever order you do will give you this. You see, rotation about x axis through alpha I minus 1, that is this, and here translation along x axis by this. So, that is this. On this side, translation along z axis by this much amount is this, okay, and rotation about z axis through an angle theta is this, right. So, now when you multiply these two things, then you get a big 4 by 4 matrix. That the contents of that matrix, the expressions, 12 expressions in that matrix is actually what is useful. So, the key point here is that this entire thing that you will get, that is these 12 things that you will have in this rotation and translation, that entire thing will be in terms of theta I or d I. Other things are also there, but other things are fixed. Okay. It is a theta I or d I which is changing, and then when you want to get into the kinematics problem, then you can describe the coordinates of the points of the last body in the series, nth body, as a product of all these rigid body motions, okay, which are the same as the corresponding poses. That is, with respect to the fixed frame, what is the position and orientation of the first frame of reference? With respect to that, what is that of the second one? With respect to that, what is that of the third one, and so on. When you multiply them in this order, which is actually meaningful in the sense that whatever is a point in the last link, to that if we multiply this, then that will show the point of that last link as described in the previous frame. That when you multiply with the yet earlier one, n minus 2 t n minus 1, then that will give it in the previous frame, and so on. So, like that as you go on till this point, then in the fixed frame you will get the location of the point in the hand, and that is of interest, because you want that point, that position of the hand to reach somewhere where it will do something. Okay. So, end effector position and orientation in terms of the joint variables. So, this actually will be found in terms of theta 1, theta 2, theta 3, etcetera, up to theta n. Now, some of these thetas will be appropriately replaced by corresponding d's if the joint happens to be prismatic. Okay. So, this problem therefore, is called the direct position kinematics, okay. And that will always be very straightforward, very simple. Just construct, given the theta 1, theta 2, theta 3 values, you can construct these and you can simply multiply it. Okay. So, this is nothing. So, this gives you mapping from joint space to task space. Why I am calling it nothing? Because it is an inverse problem which is really troublesome. Okay. So, the inverse problem will be what? So, that is the end effector position and orientation given. I want the hand of my robot to go and get hold of this bottle in this orientation. Okay. So, this position and this orientation. So, for that, what joint variable values here, here I should give. So, that is the problem of inverse kinematics, okay, inverse position kinematics. So, for that these things are given, that is xyz position of this point and phi theta psi, 3 angles which are used to represent a rotation matrix. Okay. I mean it could be roll pitch yaw, for example this is roll pitch yaw. Okay. So, rotation psi about x, then rotation theta about y, then rotation phi about z with respect to a fixed frame, or in the other order with respect to the moving frame itself, or some other equivalent representation. Okay. So, this you can find out from this information, and so then that is r is given like this and t is x y z the position, and inverse kinematics is how to find the theta 1, theta 2, theta 3 etcetera. Okay. Now, this problem actually took a long time for researchers to crack through, okay. But now it has been cracked through, I mean decades back. So, this actually has several questions in it. One is that for this you need to actually, if you think mathematically, then you say that x is a straightforward function of theta. Okay. This x is a function of this theta. Now, if given x, we have to find out theta. Then several things, several questions arise. If it is a function, then given theta, x will be always there and very clearly found. Okay. On the other hand, if x is given, you do not know whether that x is really the result of applying the function f to some theta. Okay. So, that is a question of existence. Does the solution exist? And as you know, for robot kinematics, there will be situations when the solution does not exist. Suppose I put a nice little handy robot with the base fixed here, okay, which will manipulate this glass, that remote, this water bottle and so on. Then when I want to give it a suitable point where to reach, I give the x y z coordinate which is outside the room, and say that what is the value of, what is the combination of values of theta 1, theta 2, theta 3 for you to reach that point. Obviously, it cannot reach. Okay. So, existence is certainly a problem, okay, whether solution of this problem exists. So, that is actually the workspace problem. Okay. And it is not only because that point is far away, there is another situation, the point may be too close. Give an example. With my hand, I cannot reach this point of my arm. No, I cannot. I mean, one or two people might be able to do that. Okay, that will be a terrific feat. Okay, so it may be very close. Okay. Now, if solution exists, then the second question arises: is that the only solution? Okay. Even that is not very straightforward. That may not be the only solution. Okay. For example, just standing here without moving my shoulder, there are several positions in which I can reach this bottle. You see my arm? Now see, shoulder is there only. Okay. There are several ways. So, that is another problem, that is branching, multiplicity of solutions, that is also possible. Solution may or may not exist. If it exists, then it can be multiple. Okay. And then there is a problem of selecting the correct solution. Okay. And there is yet another problem, which is in a way not much of a problem, it is a facility, but in another way it is a great problem. That is, if in order to accomplish ordinary tasks which require a certain number of degrees of freedom, if we use a robot, a manipulator which has larger number of degrees of freedom, then the solutions will not be simply multiple, but infinite. Okay. So, rather than in the space to manipulate rigid body motion tasks, how many degrees of freedom you need your manipulator to have in general? 6. Okay. 3 positions, 3 orientations, that is the dimension of this vector, output vector. Okay. In many tasks you will not need even 6. In a planar robot, which will operate always on the plane like this, there will be only 3. Okay. So, if you have a larger number of degrees of freedom for the manipulator, then that is the case in which you will have redundancy of solutions. That is quite complicated. Okay. So, what is done here, I mean what can be done is actually very complicated. There is given x, find theta. So, there what happens is that if you put that thing here, that is this you know, now find out from that one value of theta 1, one value of theta 2, the value of theta 3 from here and so on. That requires enormous calculations. That was once called the Mount Everest problem of robot kinematics. Okay. It was solved in 91, okay, by an Indian, interestingly, Raghavan. Raghavan and Roth had the classic paper in 91, in which they solved it finally, okay, and showed that it can have up to 16 solutions. So, what can be that, I mean that can be done. So, how to do that? Let me just outline. We will not do it certainly here. I mean in a normal semester course of the advanced course, we deal with it over a full lecture. Okay. So, what is done in that is that this whole thing is broken into several polynomial equations, and then one by one some of the variables are eliminated, and finally, you try to get a single polynomial equation in one of the unknowns. Okay. So, for theta 3, the quantity tan theta 3 by 2 you define as t, and in that t you can derive a 16 degree polynomial, huge long very monstrous looking polynomial equation, and by the solution of that 16 degree polynomial equation you can find 16 values of theta 3, and for every value of theta 3 then you can accordingly get the values of other unknowns, okay, other things, and that way you can show that 16 configurations are possible. Okay. So, in more simpler manipulators, for example, Puma is a simple manipulator compared to that most general case. And why Puma is a simple manipulator? What is simple in Puma? How many of you have seen a Puma robot? Must be. This is a Puma robot. Okay. So, this whole thing can rotate about this joint, that is the first joint, okay. That is the shoulder swivel, okay. Shoulder swivel, this, and then the actual arm can move about this axis, this horizontal axis, that is the arm sweep, okay, this, and then there is an elbow sweep about this, okay, and then coming here there is a wrist where there are 3 concurrent joints organized, managed in a very funny manner, okay. So, which give you the orientation. So, theta 4, theta 5, theta 6. What is simple in this? That is so for any manipulator. Any manipulator, I said, manipulating robot. What could be more general? For a robot in general, was it necessary that the first axis and the second axis are perpendicular? Was it necessary? No. So, this is something special. Was it necessary that the two joints here are parallel? Even that was not necessary. So, that is something special here. Was it necessary that the 3 axes here are concurrent? That is not necessary. Which one of these is really helpful? All are special, but the fact that the last 3 joints are concurrent, that makes the problem very simple, to the extent that at the time when the most general problem was the Mount Everest problem of robot kinematics, the Puma problem was there already in textbook. Okay. That was a research problem much earlier. That research had been cracked in early 70s. That is why Puma is one of the first robots built, because for that the kinematics was already settled. Okay. And Puma kinematics already appeared in textbook when people were actually publishing one after the other research papers to crack the general problem. So, it is the last 3 concurrent joints which was the great help in solving the robot kinematics problem. There is inverse kinematics problem. Okay, not much to do in this. Perhaps we can get rid of this screen, because now I want to discuss an example, okay, to illustrate both the process of position kinematics, that is both the process of forward kinematics and inverse kinematics. To be able to finish the example in both its aspects within half an hour, I will take a planar example, but to give you sufficiently sufficient material to think over, I will keep it as general as possible in the case of the planar case, that is I will include position and orientation both. Okay. So, how many degrees of freedom the robot must have? Minimum 3, x, y and theta. Okay. So, I want the fingers really. Okay. So, this is a robot which gets hold of things there, okay. And you can also say that whether you position it here or here, it is of not great sense, because okay, just keep it, does not matter. Okay. So, L3 we keep it. So, this link is of L1 length, this is of L2 length, this is of L3 length, and the final frame of reference is here. Okay. X here, y here and z upward, and the original, the base frame fixed. Okay. So, now link lengths are L1, L2, L3 and there is no twist angle, all of them are parallel, okay, because we are talking about a planar case. Okay. So, on the plane it is going to get things and put things there. It is like it is operating like this, picking it up here and moving like this. Okay. The way we can actually move the duster, if our arm is touching the blackboard and we move the duster to wipe. Okay. So, the position of this link, or rather the orientation of this link, can be described with the help of this angle theta 1, right. Then relative to this, the position of this link, or rather the orientation of this link, can be described by this angle, and then this is theta 3. Okay. Direct position kinematics problem will involve the finding out of this and this, right. What is the position of the hand and what is its orientation, that is at what xy point the hand is situated and in which direction is its x axis is pointed with respect to the base x axis, this angle. So, direct position kinematics would require you to find out x, y and phi. What are given? What are the things that are given? L1, L2, L3 is one set of things that is given, that is given for life, okay. Life, not our life, for that robot's life, okay. Because if we open that, disassemble that thing and rearrange them, then they will change, okay. So, for the life of that assembly, okay. So, L1, L2, L3 is given certainly. So, it is not worth even listing them in the given things. What else will be given? Theta 1, theta 2, theta 3, the variables, the input variables. So, input motors, the joints, if they are positioned at 30 degree, 22 degree and 13 degree, then where are these things? Okay. So, in order to do that, very simple, what we do? We drop a perpendicular from here, drop another perpendicular from here, and then say L1 into cos theta 1 plus L2 into cos theta 1 plus theta 2, and finally L3 into cos theta 1 plus theta 2 plus theta 3. Okay, this is L3. So, x is done. Okay. We will need these expressions tomorrow again. Then for y, we will do these things, okay, and get a similar thing. And what will be phi? Theta 1 plus theta 2 plus theta 3, right? That is very simple. This is phi. Okay. Now, the point is that direct position kinematics is solved actually, okay, and during the operation of the robot, the pertinent question is the inverse question, that is we want the robot to reach to a particular position with a given orientation, with a required orientation. For that, at what joint positions we need to put the robot. Okay. So, given x, y, phi, what are the values of theta 1, theta 2, theta 3? Now, answering that just by looking at it is not going to be possible. Okay. So, we need to solve these same three equations. Now, even for solving the inverse position kinematics problem, these equations are important, because this we now consider as a system of three equations in three unknowns and start solving. Okay. So, in equation solving we try to look for cracks. Okay. What can be eliminated from where? Okay. So, what is a pattern that is visible from which you can do something very quickly? That is later. Even before that?
Can replace with phi.
Precisely. We get this thing theta 1 plus theta 2 plus theta 3, the sum is known, phi is given. So, that phi we dump into the upper two equations, because this is something which is known. We do not know individually how much is theta 1, theta 2, theta 3, but their sum is known. Okay. So, we dump it there and get rid of this term from here. So, put it on that side. So, this and this together we have in hand. I mean, this entire business could be done with the help of those 4 by 4 homogeneous transformation matrices and so on, but that will unnecessarily clutter the whole space. For planar problems, there is absolutely no need of going to all that paraphernalia. Okay. This is x minus something. Okay. Call it x prime for the time being. Okay. Similarly, from the second equation, so, we have already eliminated one of the unknowns, theta 3 has been eliminated. Now, we have got two equations in two unknowns, theta 1 and theta 2, and as he suggested, if we square and add them, then many things can get together and get settled, and many other things get I mean come out of the thing very easily. So, as we square and add these two, so from here you will get an L1 square cos square theta 1, and from here you will get L1 square sin square theta 1. So, together that will give you L1 square. Then similarly, from here you will get one term which is L2 square cos square this plus L2 square sin square this. Now, whatever is this we do not know, but that thing is 1. So, we get this, and then the 2ab terms, that will give us twice L1 L2 cos theta 1 into cos this plus sin theta 1 into sin this. Okay. And that you know the formula thanks to our school trigonometry formula. Okay. So, that as cos this minus that, or that minus this, that minus this, same thing, because cosine, how does it matter. So, you say this minus that. So, that is theta 2. This is valuable, that turns out to be this square plus this square. Okay. Theta 1 got automatically eliminated. Okay. Theta 2 you can find out. How many values of theta 2 you will get? 2. Okay. 2 possible values of theta 2 you will get, because if 22 degrees is a valid answer, then minus 22 degrees also will be a valid answer. Okay. That makes very good sense. So, you see physically what we are doing. This we took on the other side and subtracted, that was equivalent to noting at the first step itself that in order to get oriented like this, whatever the other fellows are doing, the third link has to be oriented like this. And if we are going to position its hand here with the body oriented like this, then the starting point must be here. Then at the first step, actually the entire problem got reduced to a 2 degree of freedom problem. Okay. And what we are solving there is the 2 degree of freedom problem. That is why in the beginning I was hesitant a little bit whether to put that or not. Anyway, it goes out of the business. Now, after here, now we are telling that we are getting two possible values of theta 2. If one of them is 22 degrees, then the other is minus 22 degrees. So, compared to this position, this is clockwise 22, this is anti-clockwise 22. So, if it can be positioned here by this value of theta 1 and this value of theta 2, then it is also possible to position it at the same place with a much larger value of theta 1 and theta 2 negative value. Okay. So, these are the branches of the inverse position kinematic solution. Typically, they are called elbow down and elbow up. Okay. So, like this and like this. So, you get theta 2 two values from here, and once you get theta 2, how to get theta 1? Pardon? Yeah, not any, actually both. I will tell you why. So, that theta 2 value, if you use whichever theta 2 value you use. So, for one of the values of theta 2, since if you put it in this, okay, then you are likely to get some thing in terms of cosine, okay. And that cosine also, if you supply the value, then the angle can have two options. One of them will be valid, the other will not be valid, and which of the two is valid, you can find it out from the other one. Okay. So, that is why both are still important. So, that value of theta 1, which along with the selected value of theta 2 satisfies both of them, that is the correct value of theta 1. Okay. So, theta 1 and theta 2 we have got in hand. Now, we go all the way back to this which we had got rid of in the first step and get theta 3. This is the process to solve the inverse position kinematics problem. This was not very difficult, but this also took so much of work, okay. And actual calculation in a typical end sem exam setting takes, I mean with numbers, takes something like 10-12 minutes for even the reasonably good students. Okay. So, this much is for a planar 3 degree of freedom case, and that way you can understand that the general case will be quite complicated. Okay. Till this point, any question? Otherwise, we go to the next step.
So, theta 2 we got, and then there is one more theta 1.
That's what we were discussing, that we have to get theta 1. So, if we put that theta 2 value here, then you will get L 1 cos theta 1 plus L 2 into cos theta 1 plus something, that theta 2 is now known, equal to something known. So, this you can open as cos theta 1 cos theta 2 is known, minus sin theta 1 sin theta 2, then you will have something into theta 1 plus something into theta 2, something into cos theta 1 plus something into sin theta 1. That whole thing you can combine in a single cos or single sin. To whatever you combine, that will give out to you two values of theta 1, okay, two values of that angle, and therefore, two values of theta 1. That angle will be slightly somewhat different from theta 1. 2 values of theta 1 you will get. Okay. So, as you take one of those values of theta 1 with the selected value of theta 2 and put it here, this will not be satisfied, the other one will satisfy it. Similarly, if we had started from here, then again for theta 1 we would get 2 values, and then that when you put along with the selected value of theta 2 here, then it will not be satisfied by one set, the other set will satisfy it. The sense is that if you take 2 values of theta 2 at this stage, okay, and then from each of them if you get 2 values of theta 1, then in total there will be 4 solutions, no, but 4 solutions do not exist, because numerically solving it from here or here, this will give you 2 values of theta 1, this will give you 2 values of theta 1. Okay. So, only one of those will be common, the other one here will not be in this, the other one here will not be in this. That is why for a selected value of theta 2 you will get only one correct value of theta 1, for the other selected value of theta 2 you will get another value of theta 1. Okay. Now, this is what we do for positions. Okay. So, when we need to work out the transformation of the velocities, then what you do? You can do one very simple thing, that you can say that if this link is turned with an angular velocity of omega 1, which is actually theta 1 dot, okay, then accordingly this point will have a motion. Okay. This entire link will have a rotation, and then as this link is rotating with respect to this, for which we typically express a frame at the end of this link, then that will anyway inherit the angular velocity of this link, along with that its own angular velocity also will get added. Okay. And the motion of this will be with an angular velocity omega 1 plus omega 2, okay, and similarly for there. Okay. So, that is one way of doing it. Another way you can do it, you can straight away take these things and start differentiating. Okay. So, this is the pre-calculus original physics way of doing it, and that would be the calculus way of doing it. Both are completely equivalent, you get the same thing. Now, if you do that, then shall we get rid of this? Yes. If we do that, then we say that the linear velocity of this hand is described by x dot y dot. So, we find out the derivative of these two. Okay. So, x dot will be derivative of this plus derivative of this plus derivative of this. So, L 1 cos theta you will say minus L 1 sin theta 1 into theta 1 dot. Okay. That is derivative with respect to theta 1 and then the derivative of theta 1 with respect to time. So, that gives the derivative with respect to time plus the derivative of this. L 2 okay, minus anyway has to come. This into theta 1 dot plus theta 2 dot. Okay. Then from the last one, oh, this is L 2, no? Yeah. Then from the last one, L 3 minus L 3 sin theta 1 plus theta 2 plus theta 3 into So, when describing velocities, when studying velocities, motion, we try to club together all the terms which have theta 1 dot. Similarly, we club together all the terms which have theta 2 dot and so on. So, what we can do is that the theta 1 dot terms from here and here, if we collect together and that term I have put there, okay, and this term also will put there. Okay. Then theta 2 dot terms, if we collect together, that is from here theta 2 dot term, if I collect here, then there is no justification for this parenthesis anymore. Okay. So, now we have got x dot as something into theta 1 dot plus something into theta 2 dot plus something into theta 3 dot. This is what we expected. Okay. Similarly, y dot, by differentiation of this, you can similarly get as right, and you can get phi dot which is the angular velocity of the hand. That is very simple, theta 1 dot theta plus theta 2 dot plus theta 3 dot. And you can see that the linear velocity x dot y dot and angular velocity phi dot of the hand is available as linear combinations of the input velocities theta 1 dot, theta 2 dot and theta 3 dot. That will happen so, that will be so always in all velocity relationships. Such is not the case in the case of position relationships, which are much more complicated, involving much more nonlinearities, involving sines and cosines, and it will not be so in the case of acceleration relationships also, because there some extra centripetal and Coriolis terms come, that is acceleration of the output is not linear combination of the accelerations of the input, that is linear combinations of accelerations of input plus a few things. Those other few things are the centripetal and Coriolis components of the acceleration, but in the case of velocity relationship that holds, and that is why you can say that you can express output velocities as a linear combinations of the input velocities, and in particular you can say that I can club together x y z x y phi in a big vector capital X, that is x dot y dot y x y phi, and then its dot will be this, and that will be the coefficient of theta 1 dot from here, okay, and then into the vector of input velocities. Okay. And if you collect the coefficient of theta 1 dot from here, put it here, collect the coefficient of theta 2 dot from here, put it here, find out the component, the theta 3 coefficient of theta 3 dot from here, put it there, then you see x dot you find as this whole thing from here into theta 1 dot plus this whole thing from here into theta 2 dot plus this whole thing from here into theta 3 dot. Okay. Similarly, this fellow and this fellow, these three things when you put here, 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 then the second row gives you y dot as the correct expression, and from here coefficients are visible. Okay. So, you have got the input output velocity relationship as a linear transformation, as a matrix multiplication. And what is this matrix? What is it called? Of course, all of you know. What are the components of this? When you differentiate this with respect to theta 1 only, okay, then you get this one. So, this is theta 1 only treating theta 2, theta 3 as constants. So, this is actually del x by del theta 1, del x by del theta 2, del x by del theta 3, this is del y by del theta 1, this is del y by del theta 2, this is del y by del theta 3, and this is del phi by del theta 1, del phi by del theta 2, del phi by del theta 3. Jacobian, that is it. Jacobian, this matrix is a Jacobian, and that is why the manipulator that the matrix that you formulate out of this is the Jacobian matrix of the manipulator. So, manipulator Jacobian we have constructed. So, tomorrow we will start from this point, from Jacobian. And that same Jacobian you can frame for a 6 degree of freedom case also. That Jacobian will be 6 by 6 matrix with huge things inside. Okay. So, I think through almost. So, any questions? No questions? If questions come to your mind, then we will again meet at 11 tomorrow.